Hello and welcome back to Let's Code Physics. We are in episode 4 of our subscriber tribute, where we thank you, our 600 some odd subscribers from 60 some odd countries, by representing each country as a bouncy ball with the mass and size of the bouncy ball proportional to the number of subscribers in that country. We have successfully implemented a code where the bouncy balls are bouncing off of the walls but not yet interacting with each other. So last time we went through a little bit of math and called upon the great Wolfram Alpha to do a little bit of the algebra for us, because even as a PhD holding physicist, I don't always get my algebra correct. So what we've done is we're assuming that when the bouncy balls interact, that they're only exerting a force that goes between their center to center line, that there's no force along this perpendicular direction. What that does when we apply conservation of linear momentum and assume an elastic collision is that the perpendicular velocities will not change, and that the parallel velocities, the ones that do change, are given by these two equations down here. So what we have to do now is we have to take those and implement them into the code. So I'm going to go back over to our code. I've come down here to the while loop where we are iterating the motion and checking on the motion, updating the motion of each of the bouncy balls. So what we're going to do now is we're going to run a check on whether the current bouncy ball being considered IBB runs into any other bouncy balls. So what we're going to do is we're going to define a new counter called IBB2, and it's going to start at IBB plus 1. The reason it's starting there is that we don't need to check whether this bouncy ball interacts with itself. It's not going to collide with itself. And also because we don't need to do any double counting. So for example, if for each one, if I start from 1 and go up to number of bouncy balls, then I'm going to have combinations like 2 and 3, and then 3 and 2, and that means I'm going to double count that interaction, and I don't want to do that. Number 1, it would result in some unphysical stuff, and number 2, it costs me too much computer time. So what I'm going to do is I'm going to set up another while loop. So while iBouncyBall2 is less than or equal to number of bouncy balls. So this counter is starting at just above the current bouncy ball number and is progressing upward until it reaches the total number of bouncy balls. And what we want to do now is we want to check whether those bouncy balls are colliding with each other. The way we're going to do that is pretty simple. You'll have one bouncy ball with its radius, another bouncy ball with its radius, and we want to check to see whether their positions is within the range of their two radii. So what we have to do is we have to calculate the distance between the two. So we're going to define a new vector r, and that's just going to be the position of the first bouncy ball. Actually, I think I set it up as 2 minus 1 in the notes, so we'll say the second one. So we're going to say it's the position of the second bouncy ball minus the position of the first bouncy ball. Oops, there should be a dash, not an underscore, not a dash. There we go. IBB dot position. Cool. So this r is now a vector that describes the relative position between the two bouncy balls. We need the magnitude of that vector, so we are just going to take magnitude of r. There we go. And so what we're going to do now is we're going to run an if statement. We're going to run and we're going to check whether the distance between the two is less than the difference in their radii. So that's going to be stored as bb list iBouncyBall2 dot radius minus bb list iBouncyBall dot radius. So we're now checking as the difference between the two radii. Now this is of course a problem because if one of them is bigger than the other one or vice versa, I could get a positive or a negative. So the answer is almost always to put this difference in an absolute value. So we're going to say if the r, because r is definitely positive because it's taking the magnitude, if r is less than the absolute value of this distance, then we want it to run the collision. Now, last time we saw that the easiest way to do this is to define axes that are parallel and perpendicular to this vector r. So this is this vector r hat. So I need to define this vector r hat as r divided by r mag. All that's doing is saying this difference, r2 minus r1, divided by the magnitude. You divide a vector by its magnitude, you immediately get a unit vector. It's a wonderful thing. What I need to do now is to define their parallel components and their perpendicular components. So we're going to use this r hat in order to do that. So we're going to say v1 parallel is, and now I have to go to the velocity list of iBouncyBall. And I need to dot that. I need to take the dot product of that with r hat. The dot product is just a way of taking one vector and another vector and calculating the projection of one vector along the other one. So for example, if two vectors are perpendicular to each other, then then the dot product between the two is 0. If the two vectors are parallel to each other, the dot product is maximized. Then I need to take the perpendicular component. There's not really a trick to getting that because I don't really have a perpendicular hat, but all I have to do is take the original vector, subtract the parallel part, and the leftover must be the perpendicular part. So I just take vel list IBB and subtract v1 parallel. Oh, except that this is a vector, this is currently a scalar, so I need to multiply by r hat again, which if I'd finished reading my instructions here for myself, I would have remembered that. I literally just wrote that like 15 minutes ago, so you'd think it would be fresh in my mind. So I take these two to get the size of the component, and this r hat just assigns its direction. So think of this part in parentheses as sort of collapsing them together, and this part as projecting them along the r hat direction. Okay, so I've got, this is a vector now, this is a vector 2. And now I can do the same thing to get the parallel and perpendicular components of IBB2. All I have to do is add on some 2's. And there we go. So I don't need to change anything about r hat because I'm just defining that axis. As long as I keep that consistent, I'll be fine. And now what I have to do is I have to sort of swap these around a little bit. I have to calculate the new values. So we saw last time that the perpendicular components are going to be the same, so I'm not going to worry about those. But I do have to calculate new parallel components. So for example, what I need to do is I need a v2 parallel prime, or excuse me, I need a v1 first. So the v1 parallel prime, Wolfram Alpha was kind enough to give me as this thing. Excuse me, they're coming back. And so I'll put that into the equation here. I'll put that into the calculation here. So what I need is an M1 V1 parallel. So I take mass list of IBB times V1 parallel. Subtract from that M2 V11 parallel. So mass list IBB2 times V1 parallel. And then I add to that 2 M2 V2 parallel. So I say 2 times mass list IBB2 times V2 parallel. Okay, let's just double check that. So that should be 1 and 1, 1 and 1, minus 2 and 1, minus 2 and 1, plus 2 times 2 and 2, plus 2 times 2 and 2. Beautiful. And then I need to divide the whole thing by the total mass. So I'm going to put parentheses around the whole thing, and then just divide by mass list IBB plus mass list IBB2. Oops. And there we go. Okay, awesome. So that gives me V1 parallel prime. Now I just need V2 parallel prime, and that's going to be this piece right here. So I need a V2 parallel prime. It's going to equal, I need to take M1 over M2, so mass list IBB divided by mass list IBB2 times V1 parallel the original, which is why I had to keep the V1 parallel. I do have to actually calculate a separate prime value, plus V2 parallel, no multiplication by mass there, so V2 parallel, minus M1 over M2, so I can just copy that. Actually, instead of copying that, I could just collect these two terms. So I could have an M1 over M2 times this thing minus this thing. The reason I would want to do that is it saves my computer one calculation to have to do. So let's say minus V1 parallel prime, minus V1 parallel prime. That's the thing I just calculated. Okay, so let's double check that. So I've got M1 over M2, M1 over M2, V1 parallel minus V1 parallel prime, V1 parallel minus V1 parallel prime, plus V2 parallel, plus V2 parallel, and now I don't need this subtraction sign over there. Okay, cool. So that gets me the new components. Now I just have to combine those into to update the vectors. So we're going to say vel list of IBB. So now I'm updating the velocity of particle 1. So vel list of IBB is just going to be V1 parallel prime plus V1 perpendicular. I don't need to do anything to the perpendicular. I don't need to call it a prime because it's staying the same based on our assumption of that center-to-center force. And then I can do the same thing with IBB2. So the velocity list entry for IBB2, otherwise known as particle 2's velocity, is now V2 parallel prime plus V2 perpendicular. Cool. All right. And then I need to do something very important. I need to update IBB2, because otherwise the code will just loop around that forever, doing 1 and 2 over and over again. That was one of the mistakes I made the other day. Save that. All right, so let's double check this. So we've got our original loop for IBB. We don't need to worry about that. That is set up just fine. We've got our new counter set as 1 above the current bouncy ball number. And we're checking while bouncy ball 2 is less than or equal to number of bouncy balls. So that way it's only going to check the combinations that haven't been checked yet. We've got our relative position vector, the second position minus first position. We're taking its magnitude. And we're checking, oops, this thing is a vector. That is going to throw me an error. I need our magnitude. You've all been staring at that for the last 5 minutes, saying fix the RMAG, fix the RMAG. Less than the absolute value of the difference in the radii. So basically, if these two come within contact of each other, we're defining a unit vector r hat so that we can get the parallel components and the perpendicular components. That is 1 and IBB. That is 1 and IBB, and 1, 2, IBB2, 2, IBB2, and 1. Cool. We are calculating their new parallel components. And then we are just adding the new vector components together. Okay, and then of course this just updates the position accordingly. All right, so let's hit F5 and see whether this thing works. So if this is working, what we should see is those balls no longer passing through each other, but bouncing off of each other. And let's see what we get. Okay, so let's take a look. Oh, so I did see a collision there. Okay, let's keep an eye on USA here. Oh, I think the USA just absorbed another bouncy ball. That could be an artifact of the fact that this thing is close to the wall. Let's see. Let's check on some others. Those did not bounce off of each other. Okay. So we've got... They are still bouncing off the wall. That's good. Some of them are passing through each other. Okay, so let's... I'm going to watch for another few seconds here. It's hard to tell when the small ones collide off of the small ones. Okay, so I found the problem. Rather than the difference in the radii, I need to be taking the sum of the radii, right? Because the total distance between the centers is this radius plus this radius, not this radius minus this radius. I'm supposed to be subtracting their positions, but adding their radii. Okay, that should fix it. Let's see. Let's watch the USA over here. Bounce. Oh, that's interesting. So that sort of kept colliding with it. So it's sort of rolling around it. Oh, there we've got a cluster going on there. Okay. So I think we've got a little bit of an artifact here where they don't have enough time to bounce away from each other, so they're continuing to interact. Eventually they will all coagulate there. I think the answer to that is going to be to change our time step by a little bit. Let's multiply that by a factor of 5. Okay, that's got a little bit. So they're moving a little bit faster now. So let's actually decrease the rate by a factor of, let's decrease it by half. Okay, I'm seeing more collisions and I am seeing them stick together. That's weird. Okay, here's what I'm going to do. I'm going to put in a little check here. We are going to check these things' kinetic energies. So we are going to say kinetic energy equals kinetic energy plus the mass list IBB times mag of velocity list IBB squared. Okay, and so I'm going to set up kinetic energy equal to 0 for each part of the loop. And then within each loop, this thing is going to print for me the kinetic energy, because the kinetic energy should be conserved if I've implemented this correctly. So let's see what we get here. That kinetic energy doesn't... No, that kinetic energy is decreasing wildly. Okay. Okay, so I have spent a couple days looking over the code, and I have found the mistake. It was pretty blatant once I saw it. I also made another couple changes to the code just to make it run a little bit smoother. This part didn't necessarily help fix the mistake, but it did help avoid some of those things where the balls were curving around each other. What I'm doing now is I'm keeping track of recent collisions, and I'm doing that in this list called recent call list, so recent collision list. It starts out as all of them being false. You'll notice it's got a dimension of nBBS squared, so it represents an answer to the question of have ball IBB and ball IBB2 recently collided with each other. So that's just initializing that because at the beginning of the code they haven't had any collisions. I also made a little change here to the randomization of the initial positions. I've now made it to where they can be anywhere within a 90% range of the box length. The reason for that is you might have noticed a few times if a bouncy ball started near the wall, it would kind of wiggle back and forth. That's because it's stuck interacting with the wall there. This avoids that because it keeps them away from the edges of the wall. From the edges of the box, excuse me. So that makes that a little bit easier. Let's see. And of course, here I calculate an index. This is a really cool way to turn two labels into one label, is you just take one of the labels times the maximum value minus 1 plus the other label. I had to use that over and over again in my PhD code. I should say in my advisor's code, he used that a lot, and then I had to adopt it as well. So that's stuck in my head. But what it's doing now, in addition to checking whether the bouncy balls are within their radii of each other, it's also now checking whether there was a recent collision. So it's now only going to enact the collision code if there was not a recent collision. And so now what it does, here's the same calculation we had before. And here with the triple hash mark was the main mistake, was that I had v2 perp equal to v2's velocity minus v1 parallel. I'm sure you've been yelling at me the entire video about that, saying, no, go back to line 157, go back to line 157. Well, there it is. So I have fixed that in this line. v2 perp is now v2 minus v2 parallel. And that fixes the major mistake. And then down here, I've just added the part where it checks for whether there was a recent collision, or excuse me, so this part, it tells the list that there was a recent collision. And of course, at some point that has to get turned back to false after the bouncy balls have separated. So that's where this comes in. Else if, meaning if there was no collision this past time, check for if there was a recent collision. Then check for whether they have separated past their radii. So here we're checking whether they are now past each other. And it sets the recent collision back to false, so they're now free to collide again the next time that they meet. And so when we run the code, it now runs wonderfully. Okay. So these two did start. Oh, these two even started out close together, and they are unbinding from each other. So you notice they are now bouncing off of each other instead of swirling around each other, which is exactly what we want. Even the big bouncy ball USA that was causing us so many problems last time by absorbing other bouncy balls, they now bounce off of it. So there we go. The world is now back in harmony. So this is really fun. This is something we can play around with a little bit. So very happy to wrap up this part. Here is my tribute to you, our subscribers. In the next couple episodes, we're going to play around with this a little bit more. In the next episode, I'm going to see if I can turn this code into an ideal gas simulator, meaning can we calculate a temperature and a pressure for this thing and get the ideal gas law, or at least some semblance of the ideal gas law out. I know the ideal gas law usually applies to gases of the same type of compound. These are obviously different compounds because they have different masses, but we'll see what we get out of it. And then in the last episode in this series, we will turn the box into a three-dimensional system, and we'll watch them bounce around in 3D. I might even turn on the particle trails to see what that looks like as they bounce around. So anyway, thank you so much for watching. I'll see you next time. Bye-bye. You must really be enjoying watching these bouncy balls go back and forth. I'm going to maximize it. Oh, and then we're going to zoom out. And there we go. There we go for your full screen entertainment. This is like a game of chicken. I'll watch this as long as you will. Okay, not really. I have to go to work. Thanks for watching. See you next time. Bye-bye.